In this example, we have a solid glass sphere with a radius of 5 centimeters and an index of refraction of 1.52. It has a small coin embedded 3 centimeters from the front surface of the sphere. For the viewer looking at the coin through the glass, at what distance from the front of the glass does the coin's image appear to be located? So if we draw a picture of this scenario, we have our glass sphere, and we know that from the center to the surface of the sphere, the radius of curvature is 5 centimeters. So this distance is 5 centimeters. And we have a coin that is embedded 3 centimeters from the surface. So about right here, we have our coin, and it's 3 centimeters from the surface of the sphere. Now we have a person who is looking at the coin in the sphere. So we have our observer over here who is looking at the coin and seeing an image of the coin. Now we need to start writing down some of these quantities, assigning them to variables, and it will be very important to distinguish which quantities are positive and which quantities are negative. So we know that the light is traveling from the coin to the person's eye, since they are looking at the coin. So light is going from the coin into the observer's eye, and it will be refracted or bent by the surface of the sphere. So since light is going from the coin to the observer, light, we know, travels from front to back. So that means inside the glass is the front side, outside the glass is the back side. Another thing that we know is that light travels from material N1 to N2. So that means inside the glass is N1, or the glass has an index of refraction of N1, and the air is N2. So writing down some of these quantities, first off, we have the radius of curvature. We know the radius of curvature is 5 centimeters. And since the center of curvature is on the front side of the surface, since light is traveling from front to back, the center of curvature is on the front side, and so the radius of curvature is negative according to our sign conventions. We also know that the object, which is the coin, is located 3 centimeters from the surface, and it's on the front side, so that would be a positive, this should be S, so that would be a positive 3 centimeters. So 3 centimeters is the object distance. And then we have our two indices of refraction. So N1 is the index of refraction of the glass, and that's 1.52. And 2 is the index of refraction of the air, which is equal to 1. So we know that the principle, or the equation that we use for refractive surfaces is that N1 over S, so N1 over the object distance, plus N2 over the image distance is equal to the difference N2 minus N1 divided by the radius of curvature. So what I want to know is, where is the coin image located? So I want to know what is the image distance. And right now I can see that the image distance is buried here at in the denominator of this term of the equation. So I think what I'm going to do in order to get all this stuff out of the denominator of all these various terms is, first I'll multiply through by S. So if I multiply through by S, then in this first term, S cancels with the 1 in the denominator. Then I can multiply through also by S prime. So S prime, and S prime. And then finally, I'll multiply through by R. Of course, S prime cancels in this term. So then I multiply through by R, multiply through by R here, and R here. So the R cancels out of the denominator of this term. So then I'm left with S prime times N1 times R from this first term, plus R times N2 times S from this second term, and then from the other side of the equal sign, I have S, S prime, and N2 minus N1. All right, so now I've gotten everything out of the denominator, and I can see that I have an S prime here and an S prime here. So what I'll do next is make sure that I have all of the terms with an S prime in them on one side of the equation and all the terms without on the other side. So I would have R N2S is equal to S times S prime N2 minus N1, and then subtract off this term, so minus S prime N1 R. And then I can factor an S prime out of these two terms. So S prime, and then I would have an S times N2 minus N1, and then minus N1 R, and that's equal to R N2S. And then finally, I just need to divide both sides of the equation by this term. So S prime is going to be R N2S divided by S times N2 minus N1 minus N1R. So then I'm ready to plug in some numbers into this expression because I have all of these quantities. So R is minus 5 centimeters, N2 is 1, and S is 3 centimeters. And then in the denominator, I have the 3 centimeters times N2 minus N1, so that would be 1 minus 1.52, and then minus N1, which is 1.52, times R, which is negative 5 centimeters. So if I put all that into my calculator, do all that math, I find that S prime is going to be equal to negative 2.48 centimeters. So the negative indicates that the image is also going to be on the front side. So my image will be located somewhere here. So if this is my object, this would be my image. The image is on the front side, and it is 2.48 centimeters from the surface of the glass sphere. So next we'll want to look at a couple of consequences that we get because of refraction, because of the fact that light bends as the index of refraction changes. One of these consequences is that the atmosphere of the Earth can cause refraction, and as a result, sunsets appear to be later. So imagine we have the sun and the Earth's rotating so that the sun is setting. The sun can be at one location and it can actually be below the horizon, but as the light from the sun travels through the atmosphere of the Earth, the thickness of the atmosphere and therefore the index of refraction of the air increases as you move towards the surface of the Earth, so that the light is bent by that refraction, that increasing refractive index, and as a result the light appears to be coming from a different location. So this sunlight, even though the sun is below the horizon, the bending of the light still brings the light to a place where it can be seen, and the sun appears to be higher in the sky than it actually is. So sunsets appear to be later than when they actually occur. Another example is that of mirages. So we've all seen on a hot summer day, if you look on a road, sometimes you'll see what looks like water on the surface of the road, but then as you get closer, that appearance disappears. So what happens there is that the light just above the surface of the road is passing through very hot air. The road gets hot, the air heats up, which changes its density, changes its index of refraction. So light coming from the sky is bent by the hot air over the surface of the road, and then makes it into your eyes. And so it appears that there is sky on the road, though of course our brains interpret something that looks like sky on the surface of land as water. So it looks like to us like there's water on the surface of the road. But what we're actually seeing is an image of the sky.